All right, let's get on to the continuum radiation. Most of that is thermal radiation, thermal continuum of black body, and this is traditional plot of what spectra of black bodies look like. And that refers to a radiation field that's in a thermal equilibrium with whatever matter. So it's a completely hypothetical object except for the whole universe, which is an excellent black body. And laboratory equivalent of it will be enclosed cavity that's kept on a fixed temperature. I mean, it's a tiny little hole that doesn't disturb equilibrium too much, and radiation from it will have this spectrum. This sounds a little idealized, but in reality, actually, a lot of things look like this. And stars have spectra, not perfect black bodies, but pretty damn close. And certainly inside stars, which are optically thick, the black body radiation applies. So the quantitative description of this was invented by Max Planck, which was the other step towards quantum mechanics. And he purely empirically came up with the formula that describes the spectrum of black bodies. Now, here is the set for temperatures differing by an order of magnitude, and you can notice a couple of things. This is a log-log plot, so a straight line is a power law. And at the low frequency end, you see that they're like straight power lines, and it have slope of -2. That's called the Rayleigh-Jeans part of the spectrum. Then there is a peak, then there is a cutoff, which is exponential. And in fact, that's what Planck incorporated in his formula. He introduced quantization of energy using this constant that bears his name. And nobody understood why this formula worked until it was explained by Einstein and others. So a few things about black body spectrum. First, the peak, where the maximum is, shifts with temperature. The hotter bodies will have the peak at higher frequencies. Well, it's kind of intuitively clear. And that's called the Wien's displacement law. And there is a direct linear proportion between the two. For energies that are much less than this peak energy of Boltzmann constant times temperature, then this Rayleigh-Jeans law applies. It's roughly quadratic proportion and directly proportional to temperature. So this is often used in radio astronomy, even though the origin of the radio waves may not be thermal at all. You can still, from their intensity, you can ask what's the equivalent temperature to which this would correspond. That's called brightness temperature. Another important part about black body radiation is to compute its energy density or total luminosity of an object. It turns out that the energy density inside the black body cavity, right, or star filled with hot gas, is proportional to the 4th power of temperature. And if you let that light go, then of course the emergent flux will be then also proportional to the 4th power of temperature. And the constant of proportionality is called the Stefan-Boltzmann constant, and it's called Stefan-Boltzmann formula. So the luminosity of a given black body will be proportional to the 4th power of temperature, but also the bigger surface area, more light will get, and so it has to be proportional to the square of the radius. And so luminosity is to a really good approximation given by a formula like this. It goes as the square of the radius, 4th power temperature, aside from 4 pi, that's spherical geometry. There is Stefan-Boltzmann constant, which has this value. Now, you can measure luminosity of anything, regardless of whether it's powered by thermal radiation or not, and then you can just ask, if this were a black body, what would be its temperature to give me this much luminosity? And so regardless of what actual shape of the spectrum is, we define effective temperature as what would be the temperature of a black body that emits the same kind of luminosity. And for sun, this is close to 6,000 degrees Kelvin. And the peak of that is in yellowish part of the spectrum, and our eyes are most sensitive during the daytime to those frequencies. Isn't that amazing how evolution works? So if we lived A planet around a red dwarf star will probably be having eyes that are sensitive to near infrared. Well, black bodies do happen, actually, and the very best one known, better than any laboratory measurement, is the cosmic microwave background, which is thermal relic of the Big Bang. You can think of the whole universe as a cavity which is in thermal equilibrium. And the temperature of that radiation is 2.73 degrees Kelvin. And there are no known deviations from it. It's really remarkable. Okay, there are other kinds of continuum mechanisms. The one that's really important in astronomy is called synchrotron emission. You probably know from E&M that if an electron moves in a magnetic field that's at some angle relative to its vector of motion, there'll be Lorentz force. That means the electron will be accelerated. If it's accelerated, that means it's going to radiate. And exactly how depends on the speed. At low speeds, it will just keep going in circles, and that's called the cyclotron emission. As you increase the speed, approach the speed of light, it starts moving like a helix like this, and it shines light in a cone, which gets tighter and tighter the closer you are to the speed of light. And that's called synchrotron emission. Essentially, it's like you have cosmic accelerator. Now, spectra of synchrotron emission tend to be power law for most part. There is cutoff at both high and low end. But power law is very different from black body spectrum. And so here on a log-log plot of spectral emissivity versus frequency, you can see what typical power law, which would be slope of -1, is relative to the black body spectra. So if you kind of match them at the peak of black body, then there is excess both at low frequencies and high frequencies. And this is how we find quasars, by and large, because their spectra are not thermal. They are often close to the power spectrum. So stars don't have spectra like this, but strange things like active galactic nuclei do. And this is what they look like. These are images. Well, the top image is in radio waves at 5 gigahertz with VLA. This is a famous radio galaxy Cygnus A. You see there is a little core, which is the central engine, and there are these jets of electrons that have been accelerated close to the speed of light, and then plasma dissipates, makes these big blobs of plasma that shine in synchrotron light. So that's what sources look like in radio. The bottom one is the jet of M87, giant elliptical galaxy in Virgo cluster, and this is visible light picture. Synchrotron emission is not confined to radio. It can be X-rays or gamma rays or visible light as well as the radio. Another favorite object is the Crab Nebula. You've probably seen the picture on the right. That's invisible light. This is supernova remnant, filaments of exploded star. If you look in radio, you see something very similar, but this is not thermal emission. This is emission from electrons moving in a magnetic field that is confined to the supernova remnant. And the final source of continuum emission, which is also thermal of sorts, but not black body, is so-called thermal Bremsstrahlung, which is a German word that means breaking radiation. And for some reason, people still use that German word. It's simply you have a plasma, there's electrons and positive ions. Electron scattering off of positive ion will be accelerated. That means it's going to radiate. The higher the temperature, more of these things will happen. It goes to the square of the density. So it is essentially due to thermal motions inside this fully ionized plasma, but it's not the black body itself. But it's a continuum. And the typical places where we can see such things are, say, clusters of galaxies, which are filled with this hot gas and temperatures of millions or tens of millions of degrees Kelvin, so they're shining X-rays.